So a lot have been said on today about all this decontamination and consequences of the accident. So I will show something a little bit different. I will show how modeling exercise can complement the measurements and the tracing techniques. So the context, well, you may all be aware of these things, but I think it's important just for the presentation to recall that there was a massive, of course, release of radioactive contaminants, and cesium being the most studied. And that one important thing for the geomorphology study is that cesium has a property that once it reaches the soil surface, it is quickly and almost irreversibly bound to fine particles. So it means that it will almost not be disseminated in the soil profile. It will stay on the surface and then it will move laterally in the landscape. So that this is why we've been studying a lot of soil erosion processes, as it is the process that will mainly disseminate the contaminant in the environment. And so in the Fukushima region, only 1.5% of the initial radiocesium inventory has been exported so far, during the first 3 years, sorry, and this percentage slowly decreased afterwards. And it's been calculated that less than 1% of radiocesium has been exported between, for example, 2013 and 2016. So a lot of the stock is still there. So special patterns of erosion and sediment deposition are mainly controlled in this environment, tropical environments controlled by typhoon and land use. So these are the two main, if we summarize, the two main forcing agents that explain the movement of the contaminants. And what is fairly unique in this context, because there have been a lot of course, contamination disaster events in the world. What is a bit unique here is that the Japanese government implemented a decontamination roadmap. And so the targeted residential and cultivated areas, so the areas that are mainly in contact with people, and the technique was to remove the vegetation and the topsoil and to replace it with non-contaminated materials. So we also know that if we add the decontamination and all the climatic events, so the main fluxes of cesium in the rivers have decreased by 90% between 2011 and 2020. So a massive decrease of cesium exports in the river systems. And in contrast to this, so we have strong decontamination and strong decrease in the river systems and in the areas in contact with the people. But we have, in contrast, forested areas that have not been decontaminated, so cesium is still there. So although, of course, soil erosion on the forest is much less than soil erosion on the cropland, because forest is the main land use, it covers around 80% of the surface area. So this is still a big concern. So the objective of the study is to use this unique post-accident context to try to quantify the impact of the decontamination program and try to understand is it efficient, and if something is likely to happen in the future, what can we learn from this, from what happened in Fukushima, and how the people manage the consequences. So we first used the material that have been presented today, and so all the scientific analysis and all the monitoring that have been made, and we analyze and we use this data to calibrate and validate soil erosion models that was used to model the transport of cesium in the landscape, and then try to understand what is the part of the cesium export that is due to decontamination. So this is the study area. So Thomas showed it already. So it is the Ayama Lake catchments or the Mado Dam catchments. And blue, you can see the decontamination program area. the area that are concerned by the, so it's fairly limited in surface. It's only between 14 and 50% of the area, but it's the area that is more sensitive to erosion. And in shaded blue, you have the date, so it goes from 2014 to 2016. So here are this is the measurements. So this is what the people have measured in the river of the Mano Dam. So if we look, and there are a lot of things we can see already on these measurements. If we look on the top left, so this is the cesium concentration in the sediments. So it's not the amount of cesium, it's not the fluxes, it is the concentration of the cesium in the sediments and against time. So 3 will be 2014 and 8 will be 2019. So the first thing we can see here is that we have this decrease of export of cesium between 2014 and 2018. This is very clear. And then you have two different lines, a blue and a red. So blue is base flow. It means it's the normal runoff rate of rivers, not during typhoons or during big floods. And in red, it is during the floods. What we can see is that the concentration of sediment is higher during base flow, so when there is no flooding events. So this is quite interesting. So it means that when there is a big event, it's not only the soil surface, because if you remember, cesium is on the soil surface. It's not only the soil surface that is exported, but also rills, gullies, incisions in the landscapes. So the concentration is higher during low magnitude events. And the things we can see whole is not very clear on this graph, but maybe we can see that there are concentrations that go very high just until the fourth year after the events, so which would be 2015, 2016. So maybe there is something like decontamination we can see here, but it's not sure. It just maybe we can interpret this. If we go now on the top right, so here what we can see is not the concentration, but this is in the water, not in the sediments. So here we see the fluxes. And you have different dates. So you have the concentration of cesium against the concentration of sediments in the water. So what we can see is that the more sediment you have in the water, the more cesium you have, which is quite logical. You can also see the difference between the beginning of the timeline. So 2014 will be on the left and 2019 will be on the right. And here you can see that in terms of fluxes, it's of course the biggest event that exports the most cesium to the rivers and then to the oceans. If we go on the lower part, the two bottom graphs, and then it is a bit different here. Here, what we have the cesium concentration in the sediments according to the flow rate. And here, what we can see on both graphs, we can see that there is quite a difference between the year 2014, 2015, and the rest of the years. So maybe here again, a sign that the decontamination has been effective, but we cannot quantify it here. We can just interpret or suggest something. And we can also here find that there is a decreasing trend of the concentration of cesium with the concentration in sediment in the water. So it is again a dilution effect. So with the biggest events, so with the biggest concentration of sediment in the water, you have the lowest concentration of cesium, so which can be explained because the biggest events mobilize subsoils mainly, and not the surface soils. So as I said, we use all this data that have been collected and studied and analyzed to to elaborate, calibrate and validate a soil erosion model. So now, thanks to this model, we can replay all these years. So we can resimulate from 2014 to 2019, and we can make scenario. So here it's very simple. We made scenario of not decontamination and contamination. So we have here, you have two curves, runoff and sediments. And we have been replayed the scenes. And first, what is striking, you can see that what drives the exports in terms of sediment and runoff, it's really the big events. So we have really the temporal and punctual big exports of sediment and water when a typhoon occurs. So this is just a confirmation, and we can quantify it, and we can play different scenario and different type of typhoon to look at this. And so here we have been modeled with and without contamination. So these are the different land uses. And the biggest, the bar, the higher the land use exports sediment or cesium. So on the right, on the left, sorry, this is the sediments. So we can see that the first contribution, the contributor of sediment is the forest real. So I mean the incision in the forest. The second biggest is the forest surface soils. And then you have paddy fields, and then you have a very minor contributions of the other land use area. And what is interesting is to realize that if we look now in terms of cesium, on the extreme right, you will have with remediation, and you can see you have a shift of the importance of cesium exported from paddy field to forest. So you can here clearly identify and quantify the effect of decontamination that have been effective to diminish the exports during all the period, the export of paddy fields. So now if we look at on the all period time, so you have the time on the y-axis from 2014 to 2019, and you have three different curves. So the red curve is the measurements. So this is what have been measured on the field in the Mallet and catchments. And if we do the simulation without the remediation, you will have the blue lines. And if you replay the scenario with the remediations, and you will have the light blue lines, and you can see that it is more in accordance with the measurements. So you can here again really quantify the amount of cesium that have been exported thanks to and that will not be exported thanks to the decontamination work. So the last two graphs, and so here you have the sediment load according to time, and with and without remediation. So you can here see and calculate the difference of amount between the dotted line and the plain line. You can calculate the difference in the sediment exports during all the different typhoons. And if you go on the right now, you can see that during the decontamination work and soon after, then you will have the difference in stocks, because the particulate stocks is much lower than it would have been without the decontamination, and the decreasing trend being only with the natural decay of the cesium with time. So, and then you can calculate the stock that stay and the stock that has been removed with remediation. So thanks to this tool now, you can make scenario, and you can maybe anticipate if something is likely to happen, what will be the effect of a decontamination program of this kind of nature. So concluding remarks. So the original purpose of the decontamination in Fukushima, I've not been talking about that, but has been accomplished by reducing air dose rate. So this was the first purpose of decontamination by 30–50%. So to allow the resident return. And the contamination was also very effective to limit the migration of radiocesium in rivers, in that it targeted the most sensitive to erosion land use. So we have seen, as we said earlier, a decrease of 90% of sediment of cesium exports in the rivers between 2018 and 2020. And we could model with the modeling exercise that the decontamination of 16% of the catchment surface reduce an additional 14% of cesium exports compared to the absence of measures and physical decay alone. And this limited inventory of course reduction is mainly explained by the absence of decontamination in forest area that, just to recall, is 80% of the landscape in this region. So the forest contribution mainly occurs during typhoons, mobilizing most subsoils, so which are depleted in cesium. So which explains why the cesium concentration are lower during the big events. But the fact that we still have almost, well, nearly 70% of the cesium stock that remains on the forest constitute a major obstacle for the return of the populations that are accustomed to living in harmony with nature in this region. This has been debated already in a previous presentation. So across the special decontamination areas, covering a huge area, more than 1,000 square kilometers. So 9 million cubic meter waste was generating, that of course generating a very high cost. And until now, only a limited proportion of the initial population returned. So not only, if it has to be said, but not only biophysical studies can explain this. So this is the interest also of the MITATE Lab. So this raising a lot of questions about the overall sustainability and cost-benefit effectiveness of such a remediation program. So thank you for your attention.